Okay, so we're going to fit this up. So here's the big approximation. No longer exact, but if we do this right, we can maybe do something with it. These, by the way, are called Adams methods. Generically, when you cast it in terms of this integral formulation. So let me talk to you about one class first, which is called Adams-Bashforth. What Adams-Bashforth does is says, tell you what, how about we do the following? We will only use current time points and past points to approximate that p. You have to figure out how to approximate that function p. So how about we just make that as a rule? I can use the current point and past points. Presumably, I know these things, right? So part of the iteration is the future is what it is now, or in the past, plus something. That's it. Okay? So let's say, for instance, the easiest thing to do is say, how about p of ty? Now, if this isn't your favorite polynomial to start with, then we need to talk. But think about it for a minute. Let's just do the following. That's the simplest polynomial ever. Constant. Now, I love to integrate constants. I don't know about you, but I just take them out of the integral, and I got a dt left, and it's just so awesome. If you gave me a whole, 100 of them to do, I could just whip them out. Love that. Okay? Now, if we do this, what constant should we pick? Well, how about we pick y of n? Or sorry, the solution, we'll pick this to be this following constant. We'll evaluate the polynomial, this constant, just make it the value of f at the current time. Okay? So there's my constant. I fixed the time, I fixed the current time, and I just plug this here in to here. Now this is a constant. It comes out. I just got a t, and I have a delta t left. And when I just push this in here and I integrate, lo and behold, here's what I get. The Euler formula. Same thing I got before. Great. So in some sense, there's a sanity check that goes on here, which is like, hey, I got something I already know. All right, so let's get a little bit more sophisticated. My claim here is the higher polynomial you'll pick, and this, by the way, happens also with the fourth order Runge-Kutta, the more complicated polynomials you pick, the more accurate a representation of the solution you get. And we are actually very interested in accuracy. And so we could say, well, let's do something a little bit more fancy than this. So you might want to say, okay, so let's pick something that looks like this then. A line. After the constant, if you are forced to pick a polynomial to work with, pick a line. Okay? All right, because I can still integrate a line. You integrate t, you get t squared over 2. Okay? Okay, after that it gets really hard. Okay, but I like the constant, and so here is going to be my line. Let me tell you what my line looks like. Remember, Adams-Bashforth, I can only use current time points and past points. So my line is going to look like the following. I'll explain where I got my line in a minute. I made up a line that at time t of n, it goes through the current point, y of n. And at time t of n minus 1, it went through y of n minus 1. This kind of makes sense, right? Because my solution was at y of n minus 1, then it was y of n. And maybe I'll just draw that line between these things. So this line here goes through y of n minus 1, y of n, and let's try to make it go through y of n plus 1. Now, I have to throw this in. Remember, this is just a constant. This is a fancy-looking constant. There's the only thing I got to worry about, that t right there. And I integrate that, and I remember I get t squared over 2. I just throw that into there, and I integrate. Collect terms. What do you get? Now you get something a little fancier. Let me write it right here. Y of n plus 1 let me write it, and then I'll explain it. the solution in the future is what it is right now plus a little bit of something. And what is this little bit of something? Well, it's 3 of the current solution, evaluation of the derivative at the current time, minus the derivative 1 time ago. This is the formula times delta t that gives me predictions for the future. Turns out the accuracy of this is a second order scheme. So this here is first order. So your error is going to be globally, it's called delta t. This is delta t squared. So by doing that little extra, I drop my error a whole order of magnitude smaller in respect to delta t. Okay? Now, the problem with this Adam-Bashforth scheme, is that now whenever I do iteration, I have to use the current time and a past time. Right? So past, present, future. So that's fine, but what happens if I just give you an initial condition? I'd say, here's the solution at time 0. How do you start the scheme off? It requires 2 slices of time. There, so you can't see 2 from that. There, 2. Okay. 2 slices of time. That means what you got to do, at least at first, is do what's called a bootstrap, which means you got to get yourself a second slice of time. And then once you have 2 slices of time, you can just motor all the way forward. Okay. These are Adam-Bashforth. Let me talk about Adams-Moulton. I'll illustrate one example with Adams-Moulton. Adams-Moulton has the following rule. You are allowed to use the future point, the current point, and past points. Okay? This one only allows you to use current and past. This allows you to use the future. Now, this is an interesting concept. So I'm going to come back again and just say, well, what's my simplest constant I can pick? Well, how about the following constant? Since I have to use the future points, what I'll use is evaluate this function f in the future. Now, if I plug that in, here's what I'm going to get. Y of n plus 1 is equal to y of n plus delta t f of. Now, at first, this will seem just silly and dumb. Because you say, my future is what it is now plus a little bit of my future, which I don't know. Right? This kind of doesn't make sense to you. Why do people come up with these schemes? The reason people come up with these schemes, it's called an implicit scheme because you have your future in it. You know, you're trying to solve for this, but it's all wrapped up here implicitly. The reason people like this, these schemes typically have unbelievable stability properties when it comes to the iteration scheme. Okay? This is why people like these schemes. They're not going to go away because people will do a lot to get that stability scheme. Okay? Final comment. This is a problem. So the final comment I want to make about this is when you go to the future using the future, you want to get the power of the implicit scheme, but without having this problem of figuring out, well, I don't know what the future is. So people have come up with what are called predictor-corrector methods. Here's how predictor-corrector works. There's just a simple example there at the end of the notes we're not going to get to. But what it does is says, the problem is I don't know that. So what I can do is I can say, well, let me take my Euler technique, which predicts my future. So what I'll do is I'll first predict my future. So let's call this y of p. Now, I don't want to keep using this scheme because it's unstable often. But what I can do is predict this future point. And what I'll do is use that value of predictor point in here then to correct my future. It's kind of like Terminator. Okay, this is like the correction stage. Now, I don't know how many correctors there are because now we're on Terminator 4, right? And we really don't know the future anymore, I think.